So the next video is going to be about stress and strain, which is from chapter 14.4 in the textbook. Okay, so Robert Hooke, so he was an English scientist and he was actually a contemporary of Newton. Turns out they didn't actually get along very well. But anyway, so Hooke was interested in, well, lots of things, but in particular he was interested in how objects respond to being pulled and how they respond to being pushed, right? So imagine you have some object, say like an eraser, and think about if you push on the eraser or if you pull on the eraser, you'll notice it starts to change shape. So that's what Hooke was interested in. So that's what we're going to look at. So we need to define some things in order to be able to do that. So first off, we're going to define something called stress. So stress is force that's applied over an area. So we're going to use the lowercase Greek letter sigma to stand for stress, and it's force divided by area. So if we measure in SI units, if we measure force in newtons and area in square meters, it should be a superscript. So the SI unit for stress is the Newton per square meter. And again, tradition has it that we name units after dead white guys. So the dead white guy we name it after is Blaise Pascal. So, and it's abbreviated capital P little a. Okay, so we're also going to need to know strain. So, and strain is a change in length divided by the length. So imagine I take the eraser and let's say I squeeze the eraser and its length gets a little bit smaller. So delta L is how much smaller it gets, and L is the original length. So you divide those two and that defines the strain. And of course, well, change in length is a distance, length is a distance, so you're dividing a distance by a distance, so this is going to turn out to be dimensionless. Okay, now it's also important, there's actually several different types of stress you can apply. So first off, there's tension, right? So tension says you have an object and you pull, so you try to stretch it out, right? So if I take my eraser and I pull on either end, it stretches out. Opposite to that is compression. So compression says now you push. So I have an object and I squeeze it and the change in length gets smaller. It gets squeezed. And the other one is shear. So in sort of the classic example of shear is if you have something like a book and you apply the force perpendicular tangentially to one of the surfaces, right? So I push this way on the book, you could see the book starts to tilt, so that is a shear stress. So there's also a volume stress that we'll get to in chapter 15, which will be about the last thing we do this semester. Okay, so we talked, so there's stress, there's strain, we talked about the different types of stress you can have, and just the last thing in this video, right, so we already saw that if you start to exert these forces on an object, the object tends to deform. So, and for most objects, you can imagine making a plot of, so this is actually the strain on the horizontal axis, the stress on the vertical axis, right? So as the stress increases, the strain increases, and for most objects, there's this linear range, right, where they're directly proportional to each other. However, eventually, for most objects, you'll wind up to, right, so let's see, so first off, right, in this first range, so this is sometimes called the elastic range. And elastic just means it's reversible, right? So I squeeze on the eraser, but when I quit squeezing, it goes back to its original shape. So that's a reversible or elastic deformation. However, of course, at some point, if I apply enough stress, again, whether it's compression or tension, eventually I'll get some sort of a non-reversible deformation, right? And a non-reversible deformation is sometimes known as a plastic deformation. So that's this range of permanent stretch in the plot here. And then of course, eventually, if you just keep pushing or keep applying more and more stress, eventually it'll fracture, right? So, and eventually the plot just stops, and that's where the ultimate strength or the fracture.